Okay, today's lecture is about, we're going to give you a little topology, and this is about open sets and what they're good for. I need to really emphasize that what we're doing today is very, very dense. I'm covering a lot of material in a very short time. And I don't want you to freak out on me, okay? I know it's a lot of material in a short time. Okay, we're going to start out with some definitions. Okay, an open set. Okay, yeah, what are open sets? Well, let U be a subset of the real numbers. We say that U is open if for every A element of the set U there is a delta greater than 0 such that A minus delta to A plus delta, that open interval, is contained in U. So every point in U contains a little elbow room about it that remains in the set. Alright, now an open cover. We're going to define an open cover. Let S be a subset of the real numbers, and yet let U, this is calligraphic script U, be a set of open subsets of the real numbers. We say that this script U covers the set S, or that U is an open cover of S, if for every little s element of capital S there is an open set U sub S element of script U that contains the point S. So the elements of the set script U cover up the set S. Now here we have some more definitions. I'm going to define a partition. Okay, so we're going to start out with a closed interval from A to B. In the set of real numbers, we're going to assume that A is strictly less than B, so that this isn't just a point or the empty set. A partition of the closed interval AB is a finite subset of the closed interval AB that contains the points, the set of points A and B. For most purposes, we will use the notation that of P equal to A, the set A, which is x naught less than or equal to x1, etc., up to xn equals B. Okay, so in otherwise we're going to denote the set of the partition as x1, x2, x0, x1, x2 up through xn, and they're going to be coming in order. We will refer to the intervals composed of adjacent points as subintervals of P. Okay, so we're talking about partitions, and partitions these are different than the partitions you learn when you're talking about cosets in algebra, though they do a similar thing. The partition is like a set of walls that cuts up your closed interval into pieces. Okay, now what's the refinement of a partition? Suppose that, well, say if P and Q are partitions of AB and P is a subset of Q, we will say that Q refines P, or is a refinement of P. So it contains all the points of P, but it contains a few more, so we're chopping up the closed interval into more pieces. Okay. Given a partition of P, a partition P of the closed interval AB, we will have occasion to refer to a particular refinement of P. We will say that P prime, for instance, is obtained from P by adding midpoints if P prime is equal to P union the set of all midpoints of the subinterval. So you set out your partition P, and you just come along and you snip each of the intervals, each of the subintervals at its midpoint. Okay, we've had a lot of definitions so far, so we'd better tie them all up in a theorem somewhere, or we're just blowing smoke. So let's prove a lemma. This lemma will be used a lot in the rest of the course. Let script u be an open cover of the closed interval AB. Let P1 contained in P2, etc., be a sequence of partitions of the closed interval AB, such that for every k, P sub k plus 1 is obtained from P sub k by adding midpoints. Okay. Then there is a k such that every subinterval of P sub k is contained in some element of U. Okay, so here's the idea. You can think of P sub k as being places where you're cutting up, say, a carrot. Okay, and you have your U being a set of cups that you're covering that up. The cups being fixed in position over the carrot to begin with. You can eventually cut up P sub P, cut up your closed interval fine enough so that the cups set down over the pieces of carrot without hitting the pieces of carrot themselves. I don't know if that helps you any, but it gives me a nice visual image. We'll proceed on this to prove by contradiction. Okay. To get a contradiction, suppose that for each k element of n, there is a subinterval I sub k that is not contained in any element of U. We may assume for every k element of n that I sub k contains I sub k plus 1, because if I sub k plus 1 is not contained in any element of U, then neither was any of the subintervals of pk that contains it, and so on back up to P1. Okay, so hey, we have a nested set of intervals. Okay, by the nested interval principle, there is a unique point C that is common to all of my I sub k's. Since U covers the closed interval AB, there is a U sub C in script U that contains C. As U sub C is open, there is a delta greater than 0 such that x minus U to x plus U is contained in U sub C. There is a k element of n so that the length of I sub k is less than delta. Therefore, since C is an element of I sub k is contained in C minus delta, C plus delta. This contradicts the construction of I sub k. Remember, I sub k was chosen. It's not going to be in any subinterval, but by golly is it. Therefore, we're forced to the conclusion there is some k element of the natural numbers such that every subinterval of P sub k is contained in some element of U. Oh my God. Okay, we have just proven this brain-frying result with regards to, and rather technical, connecting open covers, which you hadn't heard about before today, and partitions, which you hadn't heard about before today. We need to walk away with something. Okay, let's take a couple of corollaries. Okay, given an open cover U, the closed interval AB, there's a finite subset of U that covers AB, and it's not difficult to prove this from what we've just done. We simply index, we simply take the elements of U that contain each of the subintervals, and we're done. They'll cover up the whole thing. For the corollary, let's suppose that U and V are open subsets of the real numbers that do not intersect each other and whose union contains AB. If A is contained in U, then V intersect AB is empty. Well, again, you here U and V would constitute a cover of the closed interval. You take the partition, it only has a finite number of elements, and then you can basically show that, hey, U contains the whole interval just by piecing together the subintervals. This one is, the proof is very visually intuitive. The first of those corollaries is basically telling us that closed interval AB is a compact set. The definition of a compact set is as follows: whenever S has the property that any open subset, that any open cover of S has a finite subset that also covers S, we say that S is compact. The second of those two corollaries was telling us that the closed interval AB is connected. Okay, to be connected means whenever S has the property that there are no disjoint open sets U and V such that S is contained in U union V, and both A intersect B and A intersect U and A intersect V are non-empty, then we say S is connected. And so compactness and connectedness are some basic properties of sets, and topological properties of sets that get a great deal of use, and we will use in this course.